Hey everyone, my name is Vikram Srikanti. I'm a PhD student in the RISE lab at UC Berkeley. Over the last few years, a lot of the research our group has done has focused on bringing performant and easy-to-use state management abstractions to serverless compute. We believe efficient state management is integral to the evolution of serverless infrastructure and cloud computing more generally, because it's a prerequisite to enable a ton of real-world applications that would like to take advantage of the simplicity and scalability of serverless computing, but are limited by the fact that standard functions as a service infrastructure today is purely stateless. The state of the art thus far has been for functions as service systems to modify application state that lives in a shared storage system like DynamoDB, which usually provides eventual consistency. This, however, raises a number of concerns around fault tolerance that have gone relatively unaddressed thus far. These are questions like what happens when functions fail mid-flight. If a function is writing multiple updates to storage and fails before all of its updates are persisted, what happens? Or maybe, more challengingly, a request is composed of multiple functions, and the first function in the request executes to completion, but before the second function can execute, there's a power outage or a DNS failure, and the second function never gets executed. In both these cases, the question is, what is the contract with the user? Who is responsible for determining that a failure has happened, and for subsequently returning the application state to a consistent view of the world for whatever the application's required definition of consistency is? Ideally, we'd like to provide the most understandable semantics possible for application developers, which is exactly once execution, meaning that logically only a single set of results from that application will ever be exposed to the outside world. However, the state of play for commercial functions as a service systems is at least once execution, which means that in the face of failures, an application's function may be retried repeatedly in order to ensure that a successful result is generated. Cloud providers encourage application developers to write idempotent code, meaning that no matter how many retries occur, the application's code will always generate the same results for a particular input. Unfortunately, we all know that idempotence is incredibly difficult for application developers to reason about. And worse yet, it's often insufficient, because in the interim between a function failing and the subsequent execution happening, the application can unwittingly leak partial side effects that were written by the previous failed version of that function to parallel requests. In practice, what we really want is not idempotence and at least once execution, but atomicity, meaning all of the updates from the function are visible or none of them are. To take a simple example, let's consider two requests, request 1 and 2. Request 1 is going to write updates to keys A and B, and request 2 is going to read keys A and B. Let's say that request 1 happens to execute first and writes an update of key A to storage. Before its update of B can be written, there is an error, and the write of B never happens. Even if request 1 is idempotent, meaning that when it is retried, it will generate the same versions of A1 and B1. In the interim, if request 2 executes and requests the read of A, it will see a new version of A, A1, but if it requests B, it will see an older version of B, B0. So in this example, request 2 has viewed some of the updates of request 1, but not all of them. Atomicity would guarantee that if there was an error, it would see A0 and B0, or if request 1 had completed successfully, it would see A1 and B1. So to recap, what we want is to provide atomic visibility of all of the updates in a request to avoid anomalies like the one we just saw. This guarantees that we never see partial executions, but only an integer number of executions. Either we see none of the results, or we see one execution where we see the results of the function that just executed. Now this makes an atomic transactional model a natural fit, meaning that if we have multiple functions that comprise a single request, what we want is to wrap them up in a single transaction and atomically commit all of the updates from that transaction at a single point in time. Now, some of you might be thinking that we can achieve this pretty easily with serializable transactions. Relational databases that provide strong consistency have been solving this problem for decades. However, those techniques often require things like coordination and membership and consensus protocols, all of which have well-known difficulties with scalability and low latencies. Unfortunately, that makes these techniques a poor fit for core autoscaling infrastructure. It would run counter to the goals of using a highly scalable and easy-to-use system like a functions as a service system if the application itself were bottlenecked by the fact that there is a strongly consistent relational database that struggles to scale past a certain point. Instead, we aimed to develop the minimum guarantee that was necessary to achieve atomic visibility to solve the fault tolerance problem for serverless functions without introducing any of the complicated techniques that make relational databases much more difficult to scale. That led us to the notion of read atomic isolation, which is a technique that was published in SIGMOD a handful of years ago. Read atomicity is a coordination-free and minimal isolation guarantee that ensures that all of the updates in each transaction are atomically visible. In practice, it prevents two different kinds of anomalies. The first is the dirty reads anomaly, which says that you shouldn't read from uncommitted, aborted, or intermediate transactions. That's an example that we just saw a few slides ago, where request 2 read A1, which was a write of request 1, but request 1 hadn't successfully committed because there was an error, and so request 2 performed a dirty read. The other kind of anomaly that read atomic isolation prevents is called fractured reads. The definition is up here on the slide, but it's a little complicated to follow. So intuitively, what fractured reads say is that you take some set of the transactions in the database and you execute them in some deterministic order. You pretend that at the end of that order, there is some set of the keys that is the snapshot that this transaction is going to read from. Now, I know that was a little difficult to follow, so let's go through a quick example. Let's say we have two committed transactions, transaction 1, which wrote K1, and transaction 2, which wrote K2 and L2. We have a client, another transaction, that's going to read K and L. If we first issue a read for K and see the version K1, and then issue a read for L and see the version L2, that is a violation of the fractured reads anomaly. The reason is because if transaction 2 executed after transaction 1, K2 would have clobbered the write of K1. And so we can either read K2 or L2, or we can read K1 in some older version of L. Now keep in mind that this isn't a strongly consistent snapshot guarantee because read atomicity is in fact a coordination-free protocol. So the set of transactions that are visible to a particular client may not be all of the transactions that have ever committed. But this is a guarantee that you never see partial effects of a transaction, which is the goal that we set out to achieve when we wanted to prevent this set of anomalies in the serverless setting. So with that said, AFT is a system we set out to build to solve this challenge by providing exactly once transactional semantics for serverless functions with minimal application level code changes. AFT does this by building on top of existing cloud key value stores like AWS DynamoDB or AWS S3, and acting as a Shim layer that transparently enforces the read atomic guarantee to make sure that all of the updates made by each logical request are atomically visible to other requests. In order to do this, we've developed new protocols under the hood to support read atomic isolation on cloud infrastructure, which involved ensuring that we were able to support read atomicity on top of shared serverless storage engines, while still ensuring coordination freeness to make sure that the system was as scalable as possible. The system itself looks something like this. It acts as a Shim layer that sits in between a serverless storage engine and a serverless compute layer. In terms of writes to storage, there's a write buffer which captures all of the updates that are made by each transaction and atomically persists them into storage at a single point in time. The protocols developed by AFT ensure that a transaction is only considered committed after all of its writes have been successfully written to storage. Similarly, there's a transaction manager that's responsible for ensuring that reads issued by each transaction conform to the prohibited anomalies, dirty reads and fractured reads, that we discussed a few slides ago. I don't have time to go into more details about how exactly each one of these protocols work, but if you're interested in learning more, we encourage you to check out the paper. In terms of performance, we found that our system was able to impose relatively small overheads compared to baseline. In this experiment, we took a simple workload comprised of two serverless functions, each of which did one write and two reads. We wrapped both of these functions in a single transaction and measured the performance of AFT as well as the performance of doing IOs directly from the corresponding storage system. Over a system like S3, which does not provide low latency and has relatively highly variable performance, we found that our protocols introduced about a 25% overhead at the median latency, which is the bar in this graph, and an extra 100 milliseconds of overhead at the 99th percentile latency, which is the whisker in this graph. However, over a system like DynamoDB, where we were able to take advantage of the batching APIs, we introduced almost no overheads compared to the version of the system deployed without AFT. And over a system like Redis, which provides much lower latencies, we had a smaller overhead of about 6 milliseconds at median and about 15 milliseconds at the tail. This was because Redis in cluster mode didn't support batching, but the relative overheads of the protocol's extra reads and writes were much lower because Redis itself is a much faster system. In compensation for paying these extra overheads and for paying the cost of doing the AFT protocols, we found that we were able to prevent a significant number of anomalies from occurring. We measured two kinds of anomalies. One was the fractured reads anomaly, which we discussed earlier in the talk, and the other was the read your writes anomaly, where within a single transaction, a application wrote a certain key, and later on, the application read a different version of the key that it had already written earlier in the transaction. What we found was that a system like S3 or DynamoDB had read your writes anomalies on almost 6% of transactions and fractured reads anomalies on about 8% of transactions. Redis, partially because it provides linearizability and partially because it is a faster system, was able to avoid a significant number of these anomalies, but still experienced read-to-write anomalies on 2% of transactions and fractured reads anomalies on almost 4% of transactions. Now, briefly, before I wrap up the talk, I wanted to highlight that AFT is a part of a broader stack that we've been working on in the RISE lab called the Hydra project, which aims to reimagine the way that we do cloud programming from the ground up. In addition to AFT, there are a couple key projects that I want to highlight. One is called Anna. It's a low-latency, auto-scaling, and coordination-free key value store that aims to provide the latency profile of a system like Redis, while also auto-scaling and matching its resource allocation to user load, similar to a system like DynamoDB or S3. Cloudburst is a stateful functions as a service system that builds on top of Anna and provides abstractions that enables application developers to write stateful applications while not compromising on performance and still achieving some simple consistency guarantees that are building on top of the consistency guarantees that Anna already provides. In addition to that, we're really excited about future work exploring richer cloud programming models that can take advantage of some of the work that we've already done here, but also push the envelope in terms of thinking about what the right way to take advantage of the scalability and resource availability in the cloud is. With that said, I'll wrap up for today, and I want to thank you for listening. If you're interested in learning more about the project, definitely go to hydraproject.github.io and feel free to reach out.